Hi everyone, my name is Elaine. I am from Brazil. I am doctoral student at Federal University of São Carlos, and today I will talk to you about my paper called Exploring Label Correlations for Partition on the Label Space and Multi-Label Classification. Here is my agenda for this presentation. First, I will talk a little about multi-label classification. Second, I will explain our proposal method. Then, I will discuss the experiment and the results. And finally, I will finish the presentation with the conclusion and future work. Multi-label classification is a predictive task of machine learning that aims to build a model that predicts multiple labels for an instance. One of the challenges in multi-label classification is to identify, explore, and model the label correlations, which helps to improve the prediction of the classifiers. The multi-label problem can be treated in two approaches: algorithm adaptation develops new algorithms or modify existing algorithms to deal with all the labels of the problem. Therefore, it is called global approach because it uses only global information to generate the model and only one classifier is needed. The transformation problem divides the multi-label problem in several sub-problems, binary or multi-class. Accordingly, several binary or multi-class classifiers are needed. This approach is also called a local approach because it uses only local information to generate the models. Also, label correlations and other information could be lost during the transformation process. In our proposal, we aim to make better use of the global and local information and overcome disadvantages of the two approaches. For that, we propose a hybrid partition. Figure 1 shows the partitions introduced here, where the square represents the partition itself, the circle represents a group of labels, and the diamond represents the label itself. Figure 1a illustrates the global partition. In this type of partition, all labels are together in a single circle. That is, a single group, and therefore a single multi-label classifier strand. Figure 1b illustrates the local partition. In this type of partition, each label is in a different circle, so each label is a group. In this example, 8 binary classifiers are trained. Finally, figure 1c illustrates the hybrid partition. Each is a partition that is in between the global and local ones. These hybrid partitions are obtained by partitioning the label space by exploring label correlations. A generated hybrid partition is composed of a group of labels where the correlated labels are grouped together. Therefore, different groups of labels with different numbers of correlated labels can be obtained, and thus different hybrid partitions. Our goal is to develop, implement, and evaluate a strategy capable of partitioning the label space, exploring the label correlations, in order to generate several hybrid partitions, and that could optimize the performance of the classifiers. Our proposal identifies, builds, validates, and tests hybrid partitions for multi-label classification using the Jacquard index to model label correlations and the class framework as a classifier. First of all, we need to divide the original dataset into training, validation, and testing using a multi-label stratification method. After that, we have phase 1, which consists of modeling the label correlations using only the label space. Table 1 shows an illustrative dataset with 5 labels. The Jacquard index is a measure of similarity that, when applied to a label space, returns a matrix with the levels of similarity between all the labels. Consider Pj a label from the label space and Qj another label. We calculate A, which returns the total number of instances that were simultaneously classified in these two labels. Then we calculate B and C that return the total number of instances classified only on the specified label, that is Pj or Qj. Finally, we divide A to the sum of A with B and C and apply this to all pairs of labels. Table 2 shows the results of Jacquard index applied to Table 1. The value 1 indicates maximum similarity, and value 0 minimum similarity. For example, label 5 has no similarity with label 2, while label 1 is more similar to label 3. As we had chosen to use an agglomerative hierarchical clustering algorithm to perform the partitioning of the label space, then we need to transform this similarity matrix into a dissimilarity matrix. For this, we apply equation 2 in table 2, and then we obtain the dissimilarity table. Now the greatest similarity is 0 and the lowest is 1. With table 3, we can already partition the label space according to the model label correlations. The agglomerative hierarchical clustering algorithm is capable of building groups of correlated labels by recursively partitioning the model label correlations. At the beginning of the algorithm, each label is in a separate group. They are grouped according to the algorithm iterates. In the last step, all labels end up together in a single group. The result obtained by an agglomerative hierarchical clustering algorithm is a dendrogram that represents the nested group of the labels and the levels of similarity where the group joins occur. To obtain different partitions, it is necessary to make cuts in this dendrogram at different levels. Figure 3 illustrates the resulting dendrogram from the agglomerative method for the sample dataset in Table 1. During the agglomerative process, the groups are measured according to a linkage metric that calculates the distance between two groups. As there are several metrics, we chose to use the traditional metrics, single, average, and complete linkage. Given the first metrics, we then use the agglomerative coefficient, which measures the quality of the generated dendrograms, to choose one of the three dendrograms to build the partitions. The linkage metric that obtains the highest coefficient value was chosen. Then partitioning is carried out. When we cut the dendrogram into 5 levels, because we have 5 labels, we get the partitions. Table 4 shows the resulting partitions. Local partition is partition 5, global partition is partition 1, and hybrid partitions are the partitions 4, 3, and 2. Once the partitions have been generated, they must be now validated. To do so, we build the training and validation sets correspond to these partitions and assimilated them to the classifiers. In our experiment, you use the class framework, which is a predictive clustering tree for multi-label hierarchical classification problems. If a group consists of a single label, then we use a local version of class. But if a partition group consists of 2 or more labels, we use a multi-label version of class. Have trained the model and validated the partitions, we need to choose one of these partitions for testing. The hybrid partition that achieves the largest macro F1 is then selected. We then built the training and testing set corresponding to the best hybrid partition and submitted to the classifiers. To carry out the experiment, we selected 10 data sets from 5 different application domains and with different characteristics. We also used cross-validation in our 10-fold experiment, so we get the results for the 10 folds in both the validation and the test. In addition, we also compared the results with 2 versions of random partitions. In the first version, we generated the partitions and the number of label groups within each partition in the same way as the hybrid partitions, but the labels are distributed randomly within each group. In the second version, we generate partitions in the same way as hybrid partitions, but the number of label groups within each partition and the distribution of labels is random. Then we build, validate, and choose the best random partitions, R1 and R2, and tested. Table 6 presents the performance results. Red indicates the worst performance and blue the better. H stands for hybrid, R1 random partitions 1, R2 random partitions 2, low local partitions, and G global partitions. we use multi-label measures based on macro and micro precision labels and macro and micro recall to analyze our results. The method that we propose finds hybrid partitions with competitive results and in some cases superior in relation to the other partitions. The Motions dataset, for example, achieved the best performance in the hybrid partitions in all 4 evaluation measures. The global partitions, in general, had the worst performance in relation to all other partitions. Table 7 shows the partitions chosen for each type of partition and for each of the 10 folds. The numbers within each cell correspond to the number of the chosen partition. For example, the dataset flags have 7 labels, so 7 partitions are generated. Partitions 1 and 7 correspond to global and local partitions, while partitions 2, 3, 4, 5, and 6 correspond to hybrid partitions. We observed that in the case of hybrid partitions, the BIRDS, ILCA, EAST, and Yelp datasets chose exactly the same partition in all 10 folds. We note that for the flags dataset, the choice was between partitions 2 and 6, but in 6 of the 10 folds, partition 6 was chosen. This is a partition that has 6 groups. One of each is composed of 2 correlated labels, while all the other 5 groups contain only 1 label. This is very close to the configuration of a local partition, and that is why the performance of these hybrid partitions is so similar to the local partitions. The same behavior is also observed in the random partitions R1, and this happens because these partitions follow the same flow of the hybrid partitions. We also observe that in the case of the BIRDS dataset, partition 18 was chosen for both hybrid and R1 partitions, but R1 performed worse. This shows that the hybrid partitions are able to improve the predictions in this case. Another result we have noticed is that it is possible for 2 highly correlated labels to be grouped together in a random partition in datasets with a small label space. For a data set with a high label space, it is likely that this will not happen. We conducted the Nemeni and Friedman statistical nonparametric tests to verify the statistical significance between the partitions. We conclude from the test that there is a statistically significant difference between the partitions in the macro and micro recall measures, and that there is no statistical difference between the partitions in the macro and micro precision measurements, as it can be seen in the graphs in figures 7, 8, 9, and 10. We concluded that hybrid partitions have obtained competitive results, but that we still need to overcome local partitions. To achieve this goal, we can evaluate the behavior of our strategy using other correlation modeling techniques, other partitioning techniques, other ways of selecting the best partition, as well as other classifiers and other datasets. We thank CAPES for financing this project. So this is it. Thank you.